Okay, welcome to my talk. My name is Rutkowski, and I'm going to tell you something about some methods about detection of Windows rootkits. Okay, and you will see. So we'll start briefly from overview of rootkits, actually Windows rootkits. So I assume that most of you are familiar with rootkit technology, so I'll try to make this introduction very short. Then I would like to say something. Yeah. Okay. So after this short introduction, I would like to say something about rootkit prevention systems, like integrity protection driver and server lock, and some bugs in these programs. Then, after we see that rootkit prevention is not sufficient, I would like to talk something about traditional detection. Oh, it's maybe too loud. Traditional detection methods, and then I will show weak points of the traditional methods, and then I would like to discuss a new approach to rootkit detection, which I call execution path analysis. Can you hear me in the last rows? No? Yeah? Okay, so let's start. So what typically rootkit can do? So basically rootkits can hide processes, which is very good action for intruder after breaking into the system. Intruder is possibly interested in hiding some processes which are running on the system, so that administrator of the system cannot detect this. So hiding processes is the basic task for the rootkit. Then hiding files or some file context, maybe on some directories, is also is often a feature of the rootkit, because we can imagine that attacker would like to hide some directories or something to keep their tools on the system which he compromised. So hiding files, hiding registry keys or real key values, adding some backdoor, some smart backdoor. So rootkit would like to hide the presence of the backdoor from the local against the local administrator, so the local administrator cannot see that something is listening on the port, and also from the remote scanning, so that the backdoor cannot be detected by, I don't know, for example, the scan by nmap from the second machine, sniffing something, etc., etc. So how rootkit can achieve its goals? We can see a basic playground for a Windows rootkit. This red line here is the border between a user space and kernel space. As you know, a system DLLs like kernel or native API are located in user space and are mapped in the process memory. And every application, or maybe not every, but most of the applications which we can... Sorry. So most applications are interacting with the system by means of system libraries. So the calls are going from the application through the libraries to the system. The basic library is native API, and native API has implemented basic functions like ZW, query system information or query directory file, etc., etc. And this implementation is based on issuing an interrupt OX to E in case of Windows 2000. when the processor encounters int instruction, it switches to the kernel mode, and the handler of the system exception is executed. And in case of Windows, this handler is kernel internal system service. And this handler dispatches the execution to the proper service function, which handles the service. So what can Rootkit do to achieve its goals? So basically, a Rootkit can hook some functions in DLL, like query directory file to hide some files. Rootkit can change some structures in the kernel memory. Rootkit can change some code in kernel memory, or can change some pointers in service table to redirect execution to some other functions, and achieve its goals. For example, when we are considering hiding files, Rootkit can, for example, hook appropriate entry in service table, which points to the function which does query directory file function, and can change this function to point to somewhere else. This other code will call the original function and then filter the output. Okay, we'll talk about these techniques later, but now I just want to make some intuition. So we can divide rootkits, as you will see later, into two main groups. Rootkits which achieve their goals by modifying execution path, and rootkits which hide something or do something else by just changing the kernel data structures. So for example, we've got some list of running processes in the kernel, and rootkits can just remove the thread object or process object from such list, and the process will be hidden. We will see such a rootkit, and we will also see how to detect this kind of rootkit. So we've got this changing only data rootkit. Okay, just before we are concentrate on these techniques and how we can detect this kind of rootkits. No.
Let me give you this.
Okay, sorry. Okay. So just before we are going to talk about this the specific techniques, I would like to make a digression about how rootkit can be installed in the system and how we can prevent doing this. So because changing kernel memory and changing some some other process memory is not something we can do in every process. So we would like to see some methods which rootkits use to install itself. So basically, userland rootkits, which modifies only these places above the red line. We can have a very depreciated rootkits with just changing some files on disks. This is typically rootkits from Unix systems, which are very depreciated today because we've got some integrity checkers like tripwire or something. So if rootkit will modify some DLL in WinNT system 32 directory, the tripwire probably will find it that something is wrong in the system. So this is depreciated. Recently, we've got some rootkits which change userland memory by in the fly runtime infection, and they are using open process function like Hacker Defender rootkit. So we can use open process function to open a process object of other process, provided we've got appropriate privileges in the system. And then we can write to this memory, so we can hook the functions in other processes. We can change the functions from the DLLs in other processes. And we can do this for every process in the system. So if we change, for example, query directory file function in every processes to not show some files on disk, or we will change query directory, or sorry, we will change query system information function to not show some processes in the system, then every process, like task manager or PS list or something else, will not show the processes which are hidden. However, userland rootkits are very easy to detect, or maybe not rootkits are easy to detect, but the processes or files or registry keys or something else which those rootkits hiding are easy to detect. Because when we look at this picture, so this kind of rootkits are just modifying functions in these boxes in light blue. So, because most applications are Win32 applications which are using this DLLs to interact with the system, so they are cheated. Yeah? So if this is task manager and is using a query system information function which is here, and this function has been hooked by rootkit, so this application won't see the out-processing the system. However, we can write our own application which will generate interrupt 2E, which is Windows system interrupt, and which will bypass this library. So if we write our own application to interact with the kernel, it will list all the hidden processes or all the hidden registry keys or something else. So it's very easy to detect such rootkits like Hacker Defender or some others. That's why the more advanced rootkits are kernel-based. So they are changing kernel data or code. So how to go to the kernel? We have a few ways to do this. First, we can write a driver and load this driver by means of official API to load driver, a Scam Manager driver, a Scam Manager API. Or we can use undocumented ZW load driver function, which actually does the same as API, because Scam Manager is calling ZW load driver function, actually. These two methods requires that the driver which we are loading has the appropriate subkey under the HKey local machine current control set system services. So we have to create the subkey and then we have to load driver. This is important that we have to create this subkey in this key, because some prevention systems, which we are going to see in a few minutes, are just blocking the possibility to create the subkeys. So if we cannot create, or if attacker cannot create subkeys under the Hacky local machine current control set system, the attacker won't be able to insert a new driver to the system, like rootkit. However, there's also a way to load rootkit to the system without creating a subkey under this registry key, and this is by means of ZW set system information function, undocumented function, which was discovered by Greg Hagland shortly after the Pedestal software has published their integrity protection driver, which disables this possibility to create this subkeys. Okay, so we've got these three ways to load the driver, kernel driver to the kernel. We've got also a possibility to write to the kernel memory directly by means of device physical memory device. We can open this device by function open section, map this section to our process memory, and write to this memory, and we are writing to arbitrary physical memory. This is not so easy as using kernel driver, because we have to translate physical addresses to linear addresses, but it is possible, and as Crazy Lord has showed in some recent frags. And there's a third way to insert code into kernel, and this is a kernel overflow. So we can, it's possible that we can find some bug in one of the hundreds of drivers, of Windows drivers, and we can exploit this bug. Possibly we can exploit this bug, and the shellcode will just insert some code to the kernel, or will modify some structures in the kernel. Okay, so these are the methods which can be used to modify kernel, or to load some malicious code in the kernel. So how to defend this installation? So this is the digression about rootkit prevention systems. First, we have something which is called driver signing in Windows 2000. And actually, this is not a good way to stop rootkits, because this mechanism was created in other purpose. It's just to ensure the administrator that he's loading the correct driver, not to stop rootkit drivers, because driver signing is not checking the signature in the .sys file, like a driver's file, but it's just checking for a signature file, and this is done only when we are installing drivers from the .env files or something like this. So driver signing doesn't actually protect against rootkits. So we've got integrity protection driver, which was probably the first effort to stop rootkits on Windows. It is from Pedestal Software. It's open source. We will talk about this in the next slide. We also have a server lock, which is a commercial product from WatchGuard, and also tries to stop rootkits. So how integrity protection driver how it's doing the protection? So IPD is a kernel driver. It hooks some system services to not allow loading new modules, new drivers. This is important that only new drivers are not allowed on the system, because Windows is using very many official drivers which have to be present on the system. So we cannot just disable the possibility to load all drivers, only the new drivers. So standard drivers from this directory, which you can see on the slide, can still be loaded. After we load the IPD into system, it activates after 20 minutes, and after this period, we cannot remove this driver. The reboot is needed. So what hooks IPD? First, some registry function like open key, create key, set value key. It hooks those functions to protect this key. And as you remember, if you would like to load the driver by official API, we have to create a special subkey in this path to describe this driver. So if we cannot do this because IPD hooked this function, we cannot use the official API to load the driver. Then it hooks open section to disallow opening device physical memory. Create file, open file are hooked to not allow to access raw disk devices like device hard disk. This is important because IPD also blocks all the files which can be found which can be found in WinNT system32 drivers directory, where are the system drivers. It opens all these files with share read attribute, so nobody can modify these files. This is important because if attacker will have the possibility to modify this one of the standard driver, he'll be able to load his rootkits. It's obvious. So device hard disk raw devices. Raw disk devices should be hooked also to, or not hooked, but prohibited to disallow the possibility to change these files. Create link object is hooked to fix some attacks, which I'm going to tell you in the next slide. Set system information is also hooked to not allow to load the driver without the subkey. And open process is hooked to not allow to runtime process infection. So rootkits like Hacker Defender will not work because a rootkit cannot open other process object and cannot change other process memory. So it looks like IPD is a very good solution. However, over this 3 years, I think 3 years, many bugs has been found in IPD. So the first bug was the problem with system information, which was the undocumented function, which was not hooked and which could be used to load a driver in the past. So after Greg Hogland has discovered this function, IPD has also hooked this. IPD staff has also hooked this function. Then we've got some attacks against device physical memory protection. I said that IPD hooks ZW open section in order to prevent opening device physical memory. However, it was possible to bypass this check by creating a symbolic link in kernel namespace. For example, /foo or something, which will be symlink to device physical memory, and then we can use open section to open /foo, and we are opening device physical memory. Because IPD was doing a string comparison of the name of the object which was opening, the attack succeeded. Then we got some bad logic in restrict enabled. It was possible to bypass the protection by just turning the clock back 20 minutes or more. It was very simple bug. Then we've got some problems with drivers directory protection. I said that IPD is trying to protect files in WinNT system32 drivers directory, so we cannot replace them, or attacker cannot replace the standard drivers. But this protection was not perfect. It was possible to bypass this protection by means of subst command. We could create a virtual drive like X, for example, and X will be a virtual drive which points to C : WinNT system32 drivers, and then we could use a copy, for example, copy rootkit.sys to X/ I don't know, PCI.sys or some IPNAT.sys. So we was able to overwrite a specific arbitrary files in the system drivers directory because the protection of this directory was also based on string comparison. After this bug has been reported, Integrity Pedestal Software change the way which are using to protect this directory, and now they are just opening those files with share read attribute. However, after they fixed this bug, there was a problem with the fact that integrity protection driver was opening all the files which was pointed by image path field in the registry. So integrity protection driver was analyzing every subkey under this current control set system service, every subkey for each driver, and IPD was reading image path field of every subkey, and this image path field is obviously is pointing to a file with the driver. So IPD has just scanning all these files and opening them with share read. However, as experience showed, some drivers do not have image path field, so they were not, the files for those drivers were not opened with share read attribute, and they could be replaced. Then was a problem with root disk access and driver file replacement, because integrity protection driver has not protects access to root devices. So we could just write the sectors on the disk on the NT file system and change those files in WinNT system 32 drivers directory. It wasn't very simple as you can think, because all of those files were in the cache. So we could replace the arbitrary files on disk through the root disk device, but after this, it was necessary to, for example, run a grep operation for 5 minutes or something to clear the cache, to clear the system cache, so the Windows will load all the drivers again, all the files again. And some more problems with symbolic link objects has also been discovered to access device physical memory. So you can see on this slide we could also create some other links, because this bug has been fixed in a way that pedestal software decided to hook create symbolic link object function, which in such a way that it was impossible to create link to device physical memory. So it was a comparison, a string comparison. If we are creating link to device physical memory, so this is not possible. But we do not have to create symbolic link to device physical memory. As you can see on this output, we can, for example, create a link to device, yeah, like hack1, and then we can open device like hack1 physical memory, and we are bypassing integrity protection driver. So recently it has been repaired in a way that integrity protection driver just hooks the symbolic link object and always returns error. So it's not possible to use symbolic link object on the system. It's not a very elegant solution, because we just disabling this functionality from the system, but it stopped the attacks. The bug history with integrity protection driver shows that it's very difficult to write such a good protection program, especially on the system with closed source like Windows, if you are not the vendor of this, or if you are not the creator of the system. However, the IPD is a very good effort, in my opinion. Even with all these bugs, which I just briefly showed, I think it's a good idea to have an IPD on the system, because is better than nothing. If we are having nothing on the system, so every module can be loaded into kernel, provided that attacker exploited some vulnerability and got administrator or system access. So it's better to have something with this host than nothing. Another protection program is a server log from WatchGuard. It's very similar to IPD. It's also a driver. It's also trying to restrict a possibility to create some registry keys in current control set system service subkey. It also protects device physical memory. It also hooks system system information, and it also has a possibility to protect some files from changes. So we have a nice dialog box, and we can choose a files like system DLLs or something else, and say that they are read-only, and nobody, including root or administrator, can modify them. It looks very nice. However, server log has also some problems. First, set system information. I said that server log prohibits the use of set system information. So, we cannot load any malicious modules. However, the policy which server log used to block the set system information usage was a little wrong, because a server log assumed that every trusted process, and trusted process is a process which was created from the file which was marked as read-only. So server log is protecting the specific file, like winlogon, for example. So winnt system32 winlogon.exe is protected from the change, and that's why server log assumes that winlogon process, which has been created from this file, is trusted. And this is wrong, because we can use open process function to modify the memory of the process in runtime. So we can use a DLL injection technique or some other technique to change the code in this winlogon process, so that it will run set system information to load our module. So we just, if we are attacker, we just, if you have a system privileges in the system, we just open process, we just using open process function to open a winlogon process object, and then we are just modifying them. We just inserting the shell code, which will load arbitrary modules for us. And winlogon.exe is able to do this because server log treats this winlogon process as trusted, and is allowed to do system information. As you can see, this has been fixed in the new version 2 months ago. However, the server log, WatchGuard company refused the details how they fixed this bug. So what's the policy is now. So the next problem with server log is that, as you saw on the previous slide, it doesn't hook open section. So user mod rootkits like Hacker Defender can be installed in the system protected by server log. Yeah, so it's not good. And also server log used to have similar problems with accessing device physical memory by means of creating some strange symlinks in kernel namespace. And as you can see at the beginning of July, so 3 weeks ago or something, WatchGuard has released a server log 2.0.4, which fixes all these bugs. However, server log do not provide the details of how they fix the errors, the bugs. So just before the summary of the prevention, even with all these programs, prevention programs, if they won't have any bugs, so if all the bugs will be fixed, you saw that the creators of prevention programs can do a very simple bugs. Some bugs are not very simple, but can be easily repaired. Some maybe not. But even if all these bugs will be repaired, and we will have an ideal integrated protection driver, for example, which cannot be bypassed by some strange symlinks or something, there's always a possible way to kernel through kernel overflow. So attacker can find some bug in the drivers and exploit this bug to load some code into the kernel. I haven't seen any proof of concept code for doing this on Windows 2000. However, it should be possible. Okay, so we see that Windows protection or another operating system protection probably never give us 100% of reliability that nobody will insert some code into the kernel. However, it will be a good idea if somebody will implement a good protection technique on Windows system, something similar to secure level mechanism from BSD systems. And as you saw, it probably would be best if Microsoft will do this. And also we see that we cannot rely only on prevention because of the kernel overflows, for example, and also because that we cannot never be sure that the prevention programs we are using do not have the bugs. We saw the bug history. The bugs have been fixed now, but some other bugs can also be in the code, but we are not knowing about them. So protection is never sufficient. That's why we also would like to have a good detection mechanism, good detection of rootkit. So this is once again the slide about how rootkit can work, and I would like now to discuss all these possible techniques which rootkit can exploit to achieve its goals. And I would like to show for every technique a method of detection such a rootkit. So once again we have this playground picture, and we start from the classic service table hooking. So the rootkit is just hooking this, just replacing some pointers in service table. Just in service table. So redirecting, rootkit is redirecting the execution path to new function which is provided by rootkit. So on this picture we can see, for example, query system information which is hooked. So probably the rootkit is trying to hide, for example, some processes on the system. So rootkit changes the pointer in the service table. So now it points to this, and this function is calling original query system information function to get the process on the system, and then we've got some filtering code which walks through the list of running processes and remove the processes which should be hidden. This is classic approach known from years. This can be easily detected. Such rootkit can be easily detected because we can have a copy of service table. So we can have a special module. System administrator can have a copy, a special module which he can insert into the system, and this module will dump the contents of the service table. So after the installation of clear system, we will save the contents of the service table to CD-ROM, for example, and then every day evening we will dump the contents again and compare if the contents has changed or not. If something has changed in the service table, it probably means that we've got a rootkit in the system. So it's very easy to detect such rootkits. That's why we can hook not service table, but we can hook exception handler. So we've got IDT, interrupt descriptor table, which has the pointers to handlers of each exception. And as I said, 2E exception is responsible for handling all the system service on Windows 2000. So we can hook this entry in IDT, and we can provide our new kernel internal system service, which will be using another service table. So we are hooking this new service table, and the original service table is untouched. So if we have this tool from the previous slide, which administrator is using to monitor if somebody has modified its service table or not, this tool will show nothing because this will be untouched. However, the system will be using this new service table, and which will result in something similar to this scenario. However, it won't be detected by such simple rootkit detectors. Okay, so we have to extend our rootkit detector to also monitor IDT table. Okay, so we've got to have a copy on CD-ROM of service table and interrupt descriptor table, and every day evening we have to compare the current service table and interrupt descriptor table with the copy of the CD-ROM. If the contents of this or this has changed, we've got a rootkit in the system. Okay, this is not enough, of course, because we can change IDTR register, because we can ask ourselves how system knows where the IDT is in the memory. So the answer is IDTR register, and IDTR register is telling the system the address of IDT table. So the attacker can modify this IDTR register to point to other IDT table and hook the second IDT table, and the original IDT table will be untouched. So depending on how we wrote our rootkit detector from the previous slide, if it has a hard-coded IDT address, it can be fooled in this way. However, if it's smart, if it's using IDTR register to find it, it won't be fooled by this technique, but it shows that it should be used IDTR to find it. However, this is still not enough because we've got some strange pointers in the kernel, which can be hooked to achieve some goals. For example, in every thread object, so every thread is representing in kernel by such a rectangle, such structure, which has some information about thread quants, so how many CPU time has been consumed by the thread, etc., etc. And one of the fields in this kthread object is telling which service table this thread is using. Normally, every pointer in this threads are pointing to this service table, which is one on the system. There's only one on the system. However, we can hook all these pointers and then the system will use the other service table. So we have something similar to this one, to this scenario, but we are not hooking IDT table, which can be monitored, which can be checked, yeah, which can be checked by the rootkit detector. But we are just hooking these pointers, system is using different service table, but rootkit detector is still monitoring this one and this table and this table. Okay, and this is still not enough to because now how to detect this. So this scenario can be detected by just having detector. We have to extend our detector to monitor all these pointers in a thread object. So at this moment, it becomes a little crazy because we have to predict all the pointers which can be hooked in the system by the rootkit, and and the change of these pointers will mean that something is wrong. So we have to, looking at the kernel, we have to choose all the pointers which can't change. So we have to choose all the pointers which are normally not changing, and their change means that the system is compromised. This is just an example of one scenario that we can use these pointers. We can change these pointers to achieve this. There are many pointers in Windows which are function pointers, which are used in some purposes, like when the system is trying to work out the running processes, it runs some specific functions. Like when process is trying to list the directory contents, it has to call some file system specific functions, and the call is through the function pointers. So this is crazy to predict all the pointers which can be changed by the rootkit. And even if somebody will do this, it's still not enough, because we can have a rootkit which does not modify any execution path, which just modify some data structures. And we've got some a rootkit, FU rootkit by FuzzenOp, which is a proof of concept rootkit, which does not hook service table, IDT table, or any other pointer. It just removes the process which we would like to hide from the active process link list. So every process object in the system has a field which is named active process link, and all the processes are linked in the list. So if we remove this process from this list, it disappeared. And when task manager is trying to acquire the list of running processes, it calls some function from system DLS, like query system information, and query system information is handled by the kernel, and kernel is walking through this list to get the list of the running processes. So if we remove the process from this list, nobody will see this process. And this is the main assumption in this rootkit. However, this is not a good way, in my opinion, to write a rootkit, because this is not exactly true that we can remove the process or something else we would like to hide, a connection or something. So let's focus on process. That we can remove process from all the lists, because we also would like our hidden process, I mean rootkit, would like that the hidden process will get CPU time. If the process will not be on any list in the system, the system scheduler or Windows dispatcher won't give a CPU time to this process. So you can ask yourself, how is it possible that a few rootkit or some other rootkits which are using this, how is it possible that this kind of rootkit just removes this process and this process gets its CPU time? Because when you run this rootkit and hide some process, you can check that this process indeed does get some CPU time. The answer is very simple. This list is not used by system dispatcher or system scheduler. There is another list. There are another lists actually, which are used by system dispatcher, and those lists which are used by system dispatcher are not grouping a process object, but are grouping a thread objects. Because in Windows, as you know, we've got a thread-based scheduler, because Windows is a multi-threaded system. So the scheduler maintains some lists which groups the running threads, and this list is called ready list head. So we've got a list of now these rectangles are not processes but are threads. So we've got all threads which are in running state. They are on the ready list head list. And also we've got threads which are in wait state, and all these threads are grouped in wait in or wait out list. So we've got two orthogonal lists. One list, active process link, which groups the processes, the running processes in the system, and this list is actually only used to, probably only used to get the list of running processes on the system. So it's for the diagnostic purposes, probably. And the second list, or second lists, are the lists which are used by a scheduler to give some CPU time to the threads, and these lists are called, like you can see on the slide. So it's very simple to detect a full rootkit or the processes which are hidden by full rootkit, because we can just read those lists which are used by scheduler. And we can almost be sure that nobody will remove the threads of the hidden processes from those lists, because then our hidden process won't get any CPU time. So yeah, this is a full rootkit. I will show you how to see this rootkit in just a few minutes. Okay, so we see that just data, because this kind of rootkit, a full rootkit, fits into this category. This is the rootkit which do not change execution path. It does not hook any function. It just changes the kernel structures. However, as I said just a minute ago, it's easy to detect such rootkit because a rootkit cannot remove, for example, processes which it would like to hide from all the lists, because the hidden objects should be running. So they must be on some other list. So we saw this kind of rootkit, a classic rootkit, direct code change. It should be obvious, because instead of manipulating pointers here, we could just change the body of this function. So it's obvious. We can just put a jump here or something, or just replace the contents of this function with the new contents. So we've got a direct code change. We've got a possibility to change some strange function pointers, like here. We can find some pointers which are used in the process of, for example, getting the listing of directory or something else, and we can change these pointers to point to some other functions, So we won't change any code, but we only change some data, and we achieve execution path redirection. Okay, we have also seen such a rootkit. However, if we write a kernel internal list reader, like I will show you in a minute, which will discover the processes hidden by rootkit by reading the dispatcher lists, it's still not reliable detector, because we can imagine a scenario like this. So we will have our rootkit will add an extra field to the let's say it's a thread object. So we've got a thread objects, and here is the object, the thread of the process we would like to hide. So we just unlinking this process from the active process link, like fu rootkit. However, it's still not enough, because we can read this dispatcher internal lists, but we can do this in this way. We can modify dispatcher code to use not this offset as a offset for example, one of these lists, like ready list head or this waiting list. So we can modify dispatcher to use a different internal list. And on this different internal list, we'll have our thread object present. So it will get CPU time. So it will be running. However, this list, this official list or the standard list from Windows, which our lister or kernel lister will be checking, will not contain our thread or hidden thread. So this won't be possible to detect this. So now we've got a question. How to detect if our system has been compromised or not, with all these techniques possible to implement. So first, I would like to divide this the situation which we are in. So if we can be an administrator which has generated some info, some system state info about the system just after the clean system installation. So we installed the system, and just before we have plugged the system into the internet, when we know that the system is clear, we're just generating some info, like service table, system service table contents, like interrupt descriptor table contents, and we are saving this on the CD-ROM. So we've got some info on the state we've got some info of the system when the system was in clear state. So this is the situation which is good, which is better than the second situation when we just come to the system and we would like to have to check if it's compromised or not, if it's some rootkit there or not. We will first focus on this situation. It's very likely that we will have the situation, because if you are administrator and you would like to have deploy some detection mechanism, we will be able probably to reinstall the system and generate some info to have it. So first we've got this comparing areas of kernel memory. So as we said, we have to have on the CD-ROM a copy of the service table, interrupt descriptor table, and probably a code area. So only code area, not data area, because we know that code is read-only. So we've got this contents or hash of this contents on CD-ROM, and every day we are checking the contents from the CD-ROM with the contents on the real system. And if somebody has hooked some entry in service table or interrupt descriptor table or just modify some code in the system, we will detect this. So it's a similar approach as tripwire. However, it's not enough because I just showed an example that we can find some pointers, like function pointers, or in this case, data pointers, like these pointers in thread objects, which points which service table is used. So attacker, we are monitoring all this, and attacker is changing these pointers, so the system will be using another service table, and our rootkit detector will fail to detect our rootkit. Okay, so kernel memory monitoring is not enough. And of course, this is not enough to detect runtime process infection, because we will have to monitor also the process dynamic libraries, so DLLs, which are somewhere here. So we will have to extend it to also check the DLLs. Okay, so this is not enough. This is not enough because we've got lots of pointers in the kernel, which are not sure where they are. However, using this, so monitoring code area, service table, and interrupt descriptor table, we can detect the service hooking and direct code change. This is a mistake. DLL hooking will be not detected by this method, as I just said. So only service hooking, direct code change. Strange functions not, and change only data structures, rootkits like foo rootkits will not be detected. Okay, so to detect this kind of rootkits, as I just said a few minutes ago, we have to have a kernel internal lister, yes, or reader, something which I will show you now. Okay. Here's a full rootkit, which I was talking about a few minutes ago. It consists of the ms.directx.sys, which is the driver which implements the rootkit, and a fu.exe, which is the interface to this driver. So I will load this driver and hide some process, and then we'll try to discover this process. Okay, now we've got the possibility to hide arbitrary process. So we'll choose one. Well, so let's hide winlogon, for example. Its speed is 204. So it's not on the list. We can also check by the task manager. As you can see, is not present. So winlogon is hidden now, and foo is doing this, removing this winlogon process from the active process link list. That's why the system cannot list this process. So let's try to read the kernel internal data, kernel internal structures to find this process, or to find out this process. So we've got a little program, a calister, which also consists of the module, kmodule.sys, which I will load. And now we can use the kernel lister to list all the processes, and we can see winlogon on the system. So although the foo rootkit has removed the winlogon process from the active process link list in the kernel, we can see this process because we are accessing this three internal kernel lists, which are used by dispatcher, and the rootkit cannot remove this process from this list, actually the threads of this process from this list, because then the process won't run. So this is the possibility to detect this kind of rootkits. Okay, so is it enough? Is it enough to have this code monitoring and process listing? This is not enough, of course, because we've got those strange pointers which we can change. So there's something else needed to detect rootkits on the system, and the approach I would like to tell now is based on execution path analysis. So the main idea here is to measure the number of instructions which has been executed during some system services. So, for example, system services querying directory contents, or querying the system for the list of running processes, or querying the system for the contents of some keys in the registry. And we are just issuing such a query, and we are counting how many machine instructions has been executed by the system. This way we can detect all the rootkits which are which based on execution path changing. So all the rootkits from this left branch. So this one we can detect by means of the calister, and for this branch we will have execution path analysis. So to implement instruction counting on Intel processor, we can use step mode. Step mode is a mode which is typically used by debuggers. And when we set trace flag in efflux register, which is 9th bit, the processor is switching to a step mode. And the step mode, when the processor is in step mode, it generates debug exception after every instruction which was executed. So this debug exception is actually interrupt number one, exception number one, and the handler of this exception, address of the handler of this exception, is stored at the IDT1. So the IDT0 is something else, IDT1 is the address of our exception. However, there's not very nice for our purpose, because TF bit is cleared when we are issuing int instruction. So if we set TF bit, so if we enable or if we switch the processor to step mode in user mode, and then we jump to kernel, the processor returns to normal mode. So we have to set it again at the beginning of the kernel code. So that's why we've got something like this. We need a special module which will hook, of course, IDT number 1, which and provides our handler for counting the instructions. So we provide a counter, like you see on the slide, which just increments some variable. And then we also hook 2e entry, so that first our let's say header is executed. So it only checks if it's executing in the contents of testing process, and if it is, it sets the TF bit. So it restores the TF bit after the transition from user mode to kernel mode. And then we are executing a standard system service. So from this point, a processor works in step mode, provided that it runs in the contents of testing process. So we've got many processes in the system. This is the user run processes, and one of these processes is our tester process. And this tester process is responsible for measuring the instructions. So for example, we've got something like start and stop here. We're starting and stopping the measurement. And here we put, for example, query system information. So here we put the code which we would like to measure to count the instructions, and we are saying start. So we are setting the TF bit. Every code here is counted, but somewhere here the processor switches to kernel mode. And when it switches to kernel mode, it runs like here. And this check here, if current bit is equal to trace bit, means if we are in the contents of this process. Not this, not this, not this, because we are going to run this tester process on the production system. So something like web server or something like SQL server shouldn't be debugged in this way, because the impact on performance will be dramatic. So only our tester processes should be debugged by the step mode. Okay, so we've got this simple picture which shows how we can manage to count the instructions. And here's the example of the test. We are running n times, like 1,000 times, a simple test. We are starting the test. We are issuing some function which we would like to count, like find first file. Find first file is a official API function to get the list to get the contents of the directory. So we are just executing this function, and we are counting how many instructions, machine instructions, has been executed. And we are saving the results. So we will have 1,000 results of this function, or number of instructions executed to do this code. So as you expect, Windows Windows kernel is a very huge program and very complicated program. So it should be obvious that we won't get the same number of instructions every time. So in the first test, it will take, for example, 20,125, and second time it will take 22,531, for example, etc., etc. So we will have many results which will be very different from each other. And even if you will calculate the average value, we'll have the average value from the first 1,000 tests, and this average value will be, for example, 20,100. And after 5 minutes, we will start this test again, and we will get the average value about, I don't know, 18,000 something else. So the differences will be huge, will be hundreds of instructions. And this is bad. This is bad because a rootkit can add a code of, I don't know, 100 instructions to achieve its goal. So 100 machine instructions is enough to filter some processes, for example, to cut some processes from the list. So if we got the noise of 300 or 500 instructions, this is bad. However, we can do something else. We don't have to, we won't calculate the average, but we will rather draw a histogram of the results. So on this axis, we'll put the test results. So for example, you cannot see this, and me too, but for example, this is, for example, 20,500, and here we've got 20,600, etc., etc. And if we've got a peak somewhere here like this, it means that, for example, 5% of tests, so it will be something like 50 execution of this test has been, or not has been, but gave exactly this number of instructions, or was consist of exactly this number of instructions. Yes. As you can see, this histograms has a very huge peaks. So it means that if it's something like 90% here, it means that 90% of tests, so like 800 tests, consist of exactly, let's say, 2,000 or 20,000, I don't know, 500 or something. This is surprising that we've got such a big peaks and such a small noise, but it can be explained in such a way that because we are executing the same system service with the same arguments, so after few hundred of execution, the system will always go through the same way. So because we can imagine the execution path of some system service as a kind of tree or something. We've got many branches, and the system, because the kernel has many if clauses. Yeah, like if something is in the cache, we can go this way. If something is not in the cache, we have to load this and execute the same instructions. So sometimes extra instructions are executed because something has to be loaded or something else, sometimes not. But if we are execute the same service with the same, if we are called the same service with the same arguments, we expect that the system caches or some variables which are using during this system service will eventually get the same values. So the system will always run the same way, the same path. And that's why we can observe the peaks, yeah? Because most of the execution of this service was directed during this path. And surprising thing is that when we issue the same test after a few hours later, with the system on, for example, heavy loaded, so in different conditions, we will observe a very similar histogram, or maybe not very similar, but with the peak at the same position. And this is very good because we can get the position of this peak, and we can treat this position of the peak as a result of the test. And if somebody will, if somebody will install a rootkit which modify the execution path, so rootkit is interested in modifying all execution paths, because rootkit wants that every time we are, for example, listing the processes, every time the processes is hidden. So rootkit will modify all the execution path. So then, if we have a rootkit on the system, we should observe that this peak will go to the right. So we just have to take the position of these peaks, save this in the file, and then every day we should do this test again and check if the position of the peaks has changed or not. We will see this in a minute. Okay, this is okay. I will show you this now, and we will talk about other things later. So now I will load the code of the driver, which adds the debug handler and hooks the system service to enable this TF bit. And now I will generate the test. As you can see, the tests are executing now, and this is a find file, this is query system information, receive, register enumerating key, and the save has been saved in a T file. Then I can issue this again and check this against T file. So the numbers you can see. Oh, sorry, I should put check here. The results are the position of the peaks. In the brackets, you have the height of the peaks, so they are very high, as you can see. And here you see that the differences are 0, so nothing is modified. So now I can load some rootkit. I will just load a very simple rootkit which just hides a file starting from hide string. It just, for demonstration purposes, it hooks query directory file function. Very simple rootkit. Sorry. As you can see, this dummy file has disappeared. It was here, file foo, hide foo, and now it's disappeared. Yeah, the rootkit is running, and let's check the system again. And now we see that 80 more instructions has been executed. We see that peak has moved 80 instructions to the right on this histogram. Yeah, so let's check some other. This is a Hacker Defender rootkit, which is recently very popular Windows rootkit. This is user mod rootkit, which just using runtime process infection. You see you see now that some files has disappeared. This rootkit has some nice features. I won't talk about this now. Just let's see if we can detect this rootkit. Oh, we can see that some extra instruction has been executed, a huge of them at 10,000, because this rootkit hides files, So it modifies find file and some others. It also tries to hide registry keys, so we can see that registry key service has executed more instructions, more instructions, and others. So okay, this approach works to detect some rootkits. However, it's not perfect. Sometimes we can see that even on the clear system, we have a small noise of few instructions executed, like 5 instructions or 15 instructions. So the position of the peak will not always be at the same exactly. Sometimes few more instructions, and it's important to have the possibility to check on a production system if this few more instructions is rootkit or is a false positive. That's why execution path recording has been added to this patch finder, and it means that not only the number of instructions is recorded, but also the exact instructions which has been executed is recorded, and we can have a dump of the traces, of the clear trace and the trace from the current system, and we can use a diff, for example, command to check which instructions has been executed, or what exactly has been executed more, comparing to the normal system, to the clear system which we have on CD-ROM. Yeah. Okay. So, is it possible to write a rootkit which won't be detected by execution path analysis? So we can think of two attacks against this technique. One attacks are against the technique at all, the general concept, and I will talk about in a minute. And the second is attacks against a specific tool. I will talk about it at the end. So first, what author of a rootkit, smart author of a rootkit can do. So first, a rootkit can hook IDT1 entry at the beginning of the rootkit code. So before the rootkit will execute its code, rootkit can hook this IDT to point to something like this. So only return. So these instructions won't be recorded by the rootkit. So only here the variable won't be incremented. We can defend this by using debug registers on Intel. We can set debug register to protect this area from writing. However, we cannot protect this area from reading because the system will blue screen. So we can protect this from reading, and we can add an extra layer here, which will jump to the origin to the handler, and we can protect this from reading and writing. So here, a rootkit cannot change this entry because it's protected, handler protected from writing, and also rootkit cannot know the address of the debug handler because this is protected from reading also. So rootkit cannot put ERET here, ERET opcode here, because rootkit do not know where it is in the memory, where it starts. So we've got something like this. The next thing attacker can do is to just disable the TF flag, or not disable in this case, to check if trace flag is set or not. If it's set, it just not execute its instructions. Okay, we can defend this, and so it won't execute its instructions because it knows that if TF is set, so somebody is tracing the rootkit, and this is not good to execute these instructions. Another way of doing this is to clear the TF bit, execute the rootkit instructions, and set TF bit again. So we won't count the instructions executed by rootkit. Defense against these attacks is very simple because there are only a few instructions which can modify efflux register. So let's say they are only popf and pushf. We can add these clauses in the debug handler to check if the next instruction is popf or pushf, so which are touching the efflux register, and if they are, we just cheating the process that the TF bit is set or not. Yes, or we just, so if the next instruction is popf, so if the program is trying, if the process is trying to pop a word from the stack and load it into efflux register, we're just setting the TF bit set TF bit in this word on the stack. So even if the process has cleared this bit to clear the TF bit, we will put the 1 in this bit, and the processor won't go to the normal mode. The stop mode will still be active. The second one, if the previous instruction was push F, so somebody has pushed the efflux register on the stack, we just clear the bit in this word on the stack. So if somebody will try to check if this bit was set or not, the process will get the false result that the trace bit was not set. It's not enough because Smart Rootkit can do something like this: set the F bit and then check if it's set or not. And if we will do something like this, a rootkit will say, okay, I set the F bit, and now the F bit is cleared because we are cheating the rootkit. So it's something wrong here, and I will skip this code. So this can be defended by just adding the extra variable, which is something like if the F is set in userland or not. And we, instead of just putting 1 every time, putting 0 every time somebody is asking about the F bit set, we will put the value of this variable. So if somebody has set this F bit set like the rootkit, we will record this, we will clear this bit, so processor won't stop the debug mode. And when somebody is asked about if this bit is set or not, we will return the value of this variable, not of the real thing. Okay, one more thing. These are the attacks against the execution path analysis concept. But however, there can be attack against a specific tool. Like you have seen a patch finder tool, and if this patch finder tool, for example, will become very popular, so then attacker can detect or can cheat the specific program. The specific program 1.1. Because attacker will have the file and will be able to find, for example, this searching for by pattern searching. Yes, if the attacker knows the binary, the attacker will know everything about this. So this is not possible to defend against such attack against specific binary. The only defense is to use a polymorphic code generator. So after administrator will download this tool, it should generate a specific version for this machine, and then it will be harder for the rootkit to detect this specific version. However, I think that for the rootkit author, it won't be profitable to do such attack against specific tool, because we can imagine many versions of this tool. We can have many tools. You can write many tools which will exploit this execution path analysis. So rootkit will have to grow. Will have to grow to contain the signatures of all the detectors. So rootkit will be similar to antivirus program. It's possibly not very practical. However, this is a theoretical way of bypass it, and the only way I see to defend against it is a polymorphic code generator. So, to summarize this, a practical detection of rootkits should combine, of course, file and registry checking like tripwire, kernel memory checking like code checking, IDT, service table. Something to show some internal kernel structures like Callister, as you saw, to detect rootkits which change only some data, and execution path analysis. So some future plans for Pathfinder to add a scheduler code test, so we will be able to find, because I didn't say about it, we can to detect something like this. So we cannot use Callister to detect this, because Callister will follow this list, which do not contain the extra thread. We have to find that Pathfinder has been patched. Sorry, not Pathfinder, but kernel dispatcher has been patched. And we can find it by specific tests, like testing wait for single object or something like this. So, so we have to add some test to test scheduler. A complete patch recording should be implemented. At the current stage, only the addresses of the instructions are recorded. So we have to use debugger now to get some instructions which were executed extra to know these instructions. More tests to detect some kernel backdoors. Yeah, maybe a possibility to test not only system services, but also to call some internal kernel function to check how many instructions they are consisting of, and if somebody has modified this. So this is good, possibly to detect some kernel backdoors, and maybe some dedicated application for comparing the traces. At current, we are using diff, just diff to detect the traces. Okay, that's all. Do you have some questions? Okay, if not, thank you.